Going back one, remember that these were the 5 different forces. If you see nothing but carbon and hydrogen, it's London forces. If you have a nitrogen, oxygen, fluorine, or chlorine with no hydrogens directly connected to the nitrogen or oxygen, then it's polar. If there is a hydrogen bonded to the nitrogen or oxygen, then that can do hydrogen bonding. If you see a salt in water, then that's that ion dipole. So the salt will dissolve in the water. That's a real strong force. And the strongest of all the forces is if it's just an ionic compound. So looking at these, HCl, what would you say is the strongest force that HCl has? Yep, so it's dipole. And the reason you know that is because there's a chlorine. Right, so nitrogen, oxygen, fluorine, or chlorine, gonna be dipole. What about CH3, CH2, CH, CH3, CH3? The one here. London forces, nothing but carbon and hydrogen, that's London forces. What about CH3CO, double bond oxygen, and then an OH? Can hydrogen bond. So the London forces, carbon and hydrogen only. So here you have an oxygen. So having the oxygens, you know, is going to make it polar, but one of those oxygens has a hydrogen. So the one that has the hydrogen attached can now hydrogen bond. So if you remember, that's a carboxylic acid. So carboxylic acids can hydrogen bond. What about MgO, magnesium oxide? Ionic. This is ionic because it's a metal and a non-metal. What about that vertical one? So this is, if you remember back, so this is glucose. So see that you have the alcohol to the right, to the left, to the right, to the right. So this is D-glucose. What can that do? It can hydrogen bond, lots of hydrogen bond. All those alcohols, anytime you have an oxygen with a hydrogen attached, so as that alcohol, hydrogen bonding. And then the last one. So the last one is KCl, calcium chloride in water. This one's the ion dipole. Ion because of the calcium chloride, so that's an ionic compound. In water, remember that the water is polar, and that's going to allow that dissolving of that salt into water. Okay, so just use those criteria for the 5. You always look for the strongest intermolecular force that's possible, because like D-glucose, it is polar. It does have dipole, but hydrogen bonding is a stronger factor that comes into play. Okay, so some of them may have more than one intermolecular force, but you always look for the strongest, because that's the one that's going to have the biggest effect on how this molecule interacts with other molecules. All right, so then we went through that golden rule of solubility. That was just that review, going back over intermolecular forces. And then we quit last time when we were talking about soaps. So remember that soaps have both polar and non-polar parts, the hydrophilic polar ionic head, and then that non-polar hydrophobic tail. So when you mix soap into water, it automatically forms those soccer balls, the spheres, which are called micelles. Okay, so we talked about like the timing. Why do you need to spend 15 to 20 seconds washing your hands? All because you need to form those micelles and give time for bacteria to be pulled off the surface of the skin before rinsing. So short hand washing, not using soap when you wash your hands, not using water. All of those things are going to end up limiting the cleaning ability that soap has. So that's sort of like what we were finishing with last time. So you look at these two. These are 2 different vitamins. Okay, we have vitamin C and we have vitamin E. Vitamin B, all the vitamin Bs. So we have vitamin B1, B2, B4, B6, B12, all the vitamin Bs and vitamin C. They all have these characteristics. Vitamin E, along with vitamin A, D, and K, tend to look more like that vitamin E molecule. So which one of these do you think is going to be polar or hydrophilic? Vitamin C or vitamin E? Which one is hydrophilic or polar?
C is hydrophilic.
So C, do you see all those oxygens? Right? So remember, oxygen's electronegative, but then I see 1, 2, 3, 4 alcohol groups. I see 4 of those OHs hanging off. So this is a hydrophilic molecule. Vitamin C can hydrogen bond because of those OHs, those 4 OH groups. Vitamin C dissolves in water. They oftentimes refer to the vitamin Bs and vitamin Cs as being water-soluble vitamins. Water-soluble vitamins are going to be hydrophilic, and all the Bs and C are hydrophilic. They're all polar, mix with water, stay mixed. But look at vitamin E. So yes, you see 2 oxygens, but what do you see a lot of? There's a lot of carbon, right? Remember all the zigzag, every single corner and an end is a carbon. So the carbons far outnumber the oxygens, those 2 oxygens in vitamin E. So this is why they say that vitamin E, A, D, and K, these are hydrophobic. These have London forces. They don't like to mix with water. They refer to these as the fat-soluble vitamins. So water-soluble vitamins are going to be vitamins that dissolve in water, and that includes the C and Bs. The fat-soluble vitamins, which is vitamins A, D, E, and K, those are oftentimes ingested within like fatty substances like fish oil. That's why like vitamin E is common, is one that you take as a fish oil supplement. And so because it's hydrophobic, it's commonly ingested in some kind of fatty substance because that's where the vitamin is dissolved in. Whereas vitamin C, you find in like orange juice, right? Which is orange juice is mostly water. So it dissolves well in the water portion of the orange juice because it's polar, because it has that ability to dissolve in water and stay mixed.
You said vitamin B is hydrophilic too?
Yep, so the hydrophilics are the Bs and the C. The hydrophobics are A, D, E, and K. And just kind of looking at the structure of the molecule, because you see so many alcohol groups in vitamin C, and you see so many carbons in vitamin E, that can help you like pick out the difference between them. Big molecules, lots of carbon, they're going to be hydrophobic because they're more like your fats and oils, those long chains. So remember that we were talking about lipids, dietary lipids. They are those hydrophobic molecules. So remember the difference between fats and oils. So a fat has more saturated, long single chains of carbon, and so they tend to be solid at room temperature, right? So this is like bacon grease, butter, lard. And do you see how when you look at that, the balls and stick structure, how that molecule, those long chains are much straighter? That allows them to pack in tighter. Oils, on the other hand, tend to have more double bonds, And those double bonds always put a bend in the molecule, so you can kind of see how that chain doesn't fit together really tight. Those three end up creating sort of a funny bend to them, and that's why these tend to be liquid at room temperature. But those long carbon chains is really why these are hydrophobic, non-polar, don't mix with water. They do have those esters. But in comparison, having just 2 oxygens, but then having 16 carbons, those 16 carbons kind of like outweigh what those hydrogens or the oxygens give in terms of polarity. But the body actually uses these hydrophobic molecules, these non-polar molecules, to create barriers. And that is really the big job of lipids, is to act as a barrier, as well as being a storage of energy, as well as being a cushion. And one of the big lipid types are what are called phospholipids. So phospholipids look a lot like a triglyceride. Do you see that they have 2 long chains of carbon? So this is the nonpolar hydrophobic part. And remember, in the zigzag, every single corner is a carbon. So this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's 18 carbons in that one chain right here. So that long chain of just carbons is why that part's nonpolar. Same thing with the monounsaturated one, the one that's got that double bond, long chain of carbon. So those are going to be hydrophobic. But this section that is on this side of the molecule, it has oxygen. It has let's count them. 1, 2, 3, 4, 5, 6, 7, 8 oxygens. But not only that, do you see that it has a positively charged nitrogen. And so once you give it a charge, now this has ionic character. And remember, like with soaps, where that oxygen had a negative charge and that made the head of the soap much more hydrophilic? This is the hydrophilic head of the phospholipid. And then they call the tails the nonpolar hydrophobic parts. So do you see how it looks like a soap molecule with an extra tail? Right? Remember, soap was like a head with just one squiggly line coming off? This one is actually a head with 2 little squiggly lines coming off because it's got 2 fatty acid chains instead of just one long chain, like a soap does. But this, while soap looks like this. And so soap kind of has more of a slight triangle shape. When you look at a phospholipid, do you see how phospholipids look more rectangular? Because those 2 tails kind of make the bottom part of the hydrophobic region a little wider. So if I take phospholipids and put them in water, they don't form a micelle. The micelle of soap molecules can be formed because the soap molecules, the head on the outside and those tails tuck on the inside. But with a phospholipid, instead of it forming a micelle, it forms what they call a bilayer. So the top layer, the outside surface of this layer, is got those polar heads pointing outwards, right? So remember that this is your hydrophilic. And so those can interact with the watery environment outside of the cell. And then you have the hydrophilic heads on the inside of the cell. That can interact with the watery environment inside the cell. So that would be salts, sugars, anything that's hydrophilic. But where those non-polar tails, I think of them, they make like a sandwich, Okay, so the heads are like the bread, and the inside of the sandwich is where the tails go. So they tuck into the inside and they make this barrier. So those tails are a barrier to anything that's what? What can't pass through? So what's not going to mix with those tails? So that whole area is hydrophobic, all of the area where the tails are. So what's not going to mix with things that are hydrophobic?
Water soluble.
Things that are watery, right? So things that are polar, things that are ionic. So this becomes a barrier to anything that's hydrophilic. So stuff that's outside of the cell cannot just pass through. I think of it like it makes an oily wall. So this becomes impenetrable to any kind of water, any salts, any kind of polar molecules, any ionic molecules. So anything that is hydrophilic, so like water, boink, bounces off. Can't pass through. Salts, so like sodium ions, bounce out. Can't pass through. So this barrier is going to block all hydrophilic. And this is how the cell controls what goes in and what goes out. So the cell starts off and just builds a barrier that most hydrophilic things are never going to get through. Watery things, sugars, salts, those water-soluble vitamins, they can't pass through. So that is why they call the phospholipid membrane, they say or refer to it as being this barrier for the cell. So here's a cell. So here's your cell, and it's got this green cover on it. So the green cover, that is the cell membrane, or the plasma membrane is another way that they refer to it. And so they show it as a blow up above. So that is a chunk of the membrane. When you look at that membrane, can you see the green heads with the two tails? Can you see the phospholipid bilayer, just like what we drew in the previous image? So the heads form this surface, the tails are sandwiched in the middle, heads form the inside layer. And this creates, so I said phospholipids, they're the barrier. So bacteria, viruses, anything water soluble can't just pass through. But now embedded in this membrane, in the phospholipid bilayer, there are these yellow things. Do you see the yellow things that look like little jelly beans almost? That is the other component that's found as part of the cell membrane. That's cholesterol. Cholesterol is found in animal cells, and cholesterol helps to make the membrane stronger. So warm-blooded animals, they need cholesterol as part of their membrane to help make that membrane strong, because you know how you warm up oil and it starts getting more fluid? Well, we don't want the barrier to become too fluid. So cholesterol actually helps to keep it a little more stable, keeps it a little stronger, still keeps things from being able to pass through. The last thing, so all the blue things that you see that are there, so those blue looking structures, those are proteins. So you would say the cell membrane is made of phospholipids, cholesterol, and proteins. So the cell membrane, the plasma membrane, is made of phospholipids, cholesterol, and proteins. So the proteins are all the bluish looking stuff. So you notice that some of those proteins look different. So some of them go all the way through the membrane. They're called integral. They go all the way through the membrane. So here's a good example of an integral protein. When you look at that integral protein, what can you imagine it would be used for? So remember we said this is a barrier, but what do you see in that integral protein? It looks like there's like a hole or a channel or a pore, like a tunnel. So it looks like there's a passageway in that integral protein. And that's one of the big jobs of integral proteins, is they let some molecules in. So they will let some molecules in or out of the cell. So for example, there are glucose transport channels. They look like that. So they look like that one that's there. And the only thing that they do is they allow glucose to pass through. So they open up, they let glucose bind, and then they let it go into the cell. So when insulin is present, those glucose integral proteins act as transporters to take glucose from the blood and allow it to go into the cell. Now, you do have to have insulin there as a requirement. So that's really one of the big jobs of those integral proteins. Notice that there's another kind of protein. Those are peripheral. Peripheral proteins, those are proteins that are found on one side or the other side of the cell. So there's an example. You can see one right here. So notice that that peripheral protein looks like it's on the inside of the cell. There's another one up here that looks like it's on the outside of the cell. Like it looks like it's attached to the outside surface. This funny looking one that's up here, up near the phospholipid bilayer word. Peripheral proteins can do a lot of things. That sometimes they act as anchors so they can help hold cells together. Sometimes they can actually be an enzyme attached to the surface of the cell. So something comes by and that binds to it and speeds up the reaction that's there. One of the big ones we've actually talked about, notice this. Do you notice that those carbohydrates? So there are proteins that have carbohydrates on them. What did we talk about where we said the pattern of the carbohydrates is important? What do you remember when talking about patterns of carbohydrates? Sometimes you can have 3 carbohydrates as the pattern, but if you have 4, then you might not be able to donate or receive this. That's all talking about what?
Refresh our memory.
Think back about it. It's in the last chapter. It's the very end of chapter 6. So we were talking about carbohydrates that are found on cells, and those act as an identifier for the cell. And so sometimes you can't give these cells to other people because they won't match.
You talking about the blood type?
Talking about blood types, A, B, and O. So there's an image right up at the top showing carbohydrates sticking off of the surface of a cell. They're attached to proteins, and that acts as an identifier. So they can be identification. Identification for a cell. And you can think of blood types as a good example of that. So if you are type O, you have a generic pattern of 3 carbohydrates. Because all other blood cells have those 3, you can give type O to anybody. But if you're type AB, then you have extra carbohydrates, and that's why you can't give type AB to anybody else. You can only give type AB to AB because theirs is such a complex number of carbohydrates. So that's a couple of examples. There's a lot more examples of what proteins do if they're found on the membrane. But big ones, integral proteins, think of channels. think of being things that allow molecules to go in and out. Think of peripheral as being ones that help to identify what the cell is. You know, when they talk about like getting transplants. So somebody needs a kidney, right? So if you need a kidney and you're looking, they will screen hundreds and hundreds of people just checking to see what is the pattern of proteins on the outside of your kidneys. Okay, within the cells of the kidney, they have to look at all of the surface markers on the cell of specific kidney cells, and then they try to find a match. They say that those markers have to match at least 80%, or your immune system will attack and destroy that donated kidney. So it's that specific. Same thing like if you've ever heard about people that like have to go and like do bone marrow transplants, that have to have an organ, that need to even get tissues oftentimes. But those peripheral proteins, they have to make sure that the patterns on them match between the donor and the recipient so that you don't end up with rejection. Okay, so we have integral proteins, peripheral proteins. A little more about cholesterol, because this is really what finishes up chapter 7. So cholesterol, I said, it is found as part of the cell membrane. Cholesterol is a component that's called a steroid. So a steroid is any molecule that has this basic shape. So if you've ever been super sick and you've gone to the doctors and they give you cortisol, okay, they either give you a shot in the bum, a cortisone shot, and you like feel 100% better within 6 hours. You're like, oh, I feel so much better. Or maybe you had to take a series of steroids. So one day you took 4 pills, next day you took 3, next day you took 2, next day you took 1. They do that a lot, like if you have to have like a tooth extracted. So the steroid, those steroids help to sort of like stimulate your immune system, help you recover and repair faster. So those steroids are very similar to cholesterol. Cholesterol's big job, though, is like I said, it really just helps to stabilize the structure of the cell. You get cholesterol in a couple of ways. So it helps to improve the stability of the membrane. That's its big job. And the one thing to remember is that only warm-blooded animals make cholesterol. So plants do not make cholesterol. They don't need to, because the plants outside, the grass outside, can grow at the environmental temperature. So like today, at 45 degrees, the grass can still grow. It's not going to grow really fast. You would not grow if you were 45 degrees Fahrenheit. We are warm-blooded, so we stay at 98.6. So warm-blooded animals have a higher body temperature than plants. Warm-blooded animals need cholesterol to make sure that that membrane stays strong. Cholesterol can also get converted to other molecules. So cholesterol can get converted to testosterone. What's testosterone? What do you associate with testosterone? Men. It is the male sex hormone. So testosterone secretion increases at puberty, and it causes body hair, it causes like facial hair, it causes the skin to get thicker, it causes the larynx to enlarge so their Adam's apple gets bigger. Testosterone increases the amount of growth hormone and growth that occurs and doesn't close their growth plates very quickly. That is why males grow longer and end up being taller in the long run. But here's an interesting thing, estradiol. Estradiol is one of the estrogens. So there's about 6 estrogen hormones that females make. Estrogen is what? It is kind of the counterpoint to testosterone. Estrogen is the female sex hormone. So testosterone is made by the testes, estrogen is made by the ovaries. Estrogen causes the changes that are associated with becoming more feminine at puberty. So there you get breast development, body fat development changes. Females don't typically get the big Adam's apple because Estrogen doesn't cause that. Females don't get the super thick, kind of coarse body hair that men get because estrogen doesn't do that.
Because, well, some women can grow mustaches and beards. How's that possible?
So that is oftentimes because of abnormal testosterone secretion. So it's kind of like a balance. So it is sort of a balance of females, both males and females secrete both of them. But females secrete much higher estrogen content than testosterone. Males secrete much higher testosterone content than estrogen. But they're both there. It's just one's much greater. And so what happens, why you might see women, so one, it could be medications. Some medications can cause abnormal hair growth, but also as you reach menopause, so that's going on 50, that is when estrogen levels begin to go down, and that's when testosterone may start to show some characteristics. So those are those irritating chin hairs. So you're like, why do I have this black hair that's growing on my chin? I got
gray.
Yeah, so that's why, is because as you approach menopause, estrogen begins to go down. And so then you start to see more of like the side effects that testosterone would have caused. So that's why it's not uncommon. But there are some medications that will actually stimulate abnormal hair growth, like hair growth that you wouldn't expect. There are some imbalances like Cushing's disease. There's some pituitary, Yeah, some pituitary imbalances that can trigger higher testosterone levels produced in a female, and so then they can have more body hair than what they would otherwise. But the thing that's craziest to me is look at how similar they are, estrogen and testosterone. Do you see they both have the steroid nucleus? They both have those 4 rings linked together. So there's just a couple of things that are different between the two of them. But they cause such huge different changes at puberty. It's just amazing to me. I would think that estrogen would look nothing like testosterone, but they're in fact very, very similar. And they're both made from cholesterol.
That explains why men have breasts.
Well, a lot of that has to do with like body fat deposits. Like it just. All right, you saw a man today. Well, it's just sometimes different, like it's different females too. Like there's some women that are kind of apple shaped because they store more body fat in their abdomen. And some women have more body fat in their bum and in their thighs. Like it's just like differences. Same thing with men. It's the same, you see, you see differences otherwise. So sex hormones, you need cholesterol to be able to make those sex hormones. You need cholesterol in order to be able to make stress hormones. So the stress hormones, like cortisol, come from the adrenal glands, epinephrine, norepinephrine. They're very similar, and cholesterol is used to build them. So why does cholesterol considered like so bad? Like, when they talk about, I went to the doctor's and they tested my cholesterol and it's bad, it's too high. Okay, so when they talk about cholesterol, cholesterol is a measurement, it's a circulating molecule in the blood. Total cholesterol optimally should be less than 200 milligrams of cholesterol per deciliter of blood. So they just tell you, my doctor said my cholesterol is 250. Okay, but it actually is a measured value. It's 250 milligrams of cholesterol per deciliter of blood. And that, keeping it under 200 is optimal. But now, cholesterol is hydrophobic. So cholesterol cannot freely float through the blood. Because what do we know about polar and non-polar? You put them together, they're gonna separate. So cholesterol cannot freely float. It's not soluble in water. So it has to have a carrier. So the carriers are really what they measure when they test your cholesterol. There's like 5 of them, but the 2 most common carriers are HDL and LDL. HDL just stands for high density lipoproteins. So this is where HDL comes from. high density lipoproteins. This is the cholesterol carrier. Yeah, they're the good ones. The cholesterol carriers that transport cholesterol to a destination. So it might take cholesterol and transport it to the fat cells for storage, or it might take cholesterol and send it to cells that are growing because they need to build more membrane. Or it might take cholesterol and send it to the sex organs so that they can make estrogen or testosterone. So I always think of HDL, it's like the cholesterol with a purpose. So it's on its way going somewhere. This cholesterol is not released in the blood vessels. It is held on too tightly so that it can go from one place to another. So you can think of it as being transported cholesterol. LDL, low density lipoproteins, are different. Low density lipoproteins are really circulating cholesterol. So it is just moving through the blood without really any type of destination. So as it moves through the blood, this carrier doesn't hold on to cholesterol very tightly, and it can release it. And if it releases it, cholesterol is not going to stay dissolved in the blood. Cholesterol is going to stick to the wall of the blood vessel.
What is that word?
Where? It says cholesterol carriers that transport cholesterol to a destination, not released in the blood. Whereas LDL, this is cholesterol that circulates, and this can be released in the blood, and if it does, it's going to stick to blood vessels. So here's the example below. So this shows a blood vessel, and so normally you have blood that just flows through. So as these LDL carriers pass through, they can drop cholesterol, can come off of them or out of them, and if it does, then it begins to stick. They call this plaque. So plaque is cholesterol and fat that begins to collect on the wall of a blood vessel. And it's connected to levels of LDL. So if you go to the doctor and they measure your cholesterol and they say your LDL levels are high, that indicates that you have a higher incidence of fat that is beginning to collect along the blood vessel wall. So if there's a little, still blood flows pretty well. But look at the bottom image. So looking at the bottom image, what problems do you see? Yeah, so this is going to cause the blood vessel to narrow. So can as much blood pass through? No. And so this is going to slow circulation. So you're not going to get good blood flow through an area where there's this type of blockage. Slowing circulation means you slow oxygen and nutrients to the cells that are on the other side of this plaque material. If this is in the heart muscle, what could this cause? A heart attack. So this could block blood flow to the point that blood doesn't get to the heart muscle and you can end up with a heart attack. What about if it's in blood vessels that supply the brain? That can increase the risk of stroke. So stroke can occur. So because of this is why if your cholesterol levels are elevated, the doctor might be concerned. Optimal, so we said optimal ratio. If your cholesterol's just under 200, so say that it's like 180, okay? Optimally, you want your cholesterol, the HDL, to be higher than your LDL because HDL is the cholesterol carrier, doesn't let it go. In fact, HDL can pull cholesterol off the wall of vessels. So that's why HDL has always been called the good cholesterol. It transports cholesterol. It can help to remove plaque off of the walls of blood vessels. It's associated with sort of good and healthy cardiovascular health. LDL, you want to limit your LDL. You want your LDL optimally to be less than half of your total cholesterol number because LDL is the one that causes plaque. And so that is why they've always called LDL the bad cholesterol. So where does it come from? Okay, well, cholesterol comes from your diet. If you eat any kind of animal products, there's cholesterol because cholesterol is in warm-blooded animals. So if you eat anything that comes from a cow, anything that comes from a pig,
Eggs.
anything, chicken, and including eggs, okay, anything that comes from an animal, cholesterol. Okay, because animals make cholesterol. So if you go to the doctor and they say your cholesterol is 250 and your LDL is 120 and we're concerned, okay, well, that might be a legitimate concern. So one way that you can help lower cholesterol is start to lower your dietary intake of meats. Meats are not all the same though. It's really based on their temperature. So remember, the warmer your body temperature is, the more cholesterol you need to keep the cell membrane stable. Cows have a body temperature of about 102. So they have a higher body temperature even than we do. So what do you think they have for cholesterol? They have more. Okay? So cows, red meat is the highest. And so that also includes dairy, because that comes from a cow. Okay, so red meat, dairy, butter also comes from a cow. Any kind of cow product, they're going to have higher cholesterol content. Next, under that are pigs. Pigs are closer to our body temperature, so they're a few degrees lower. So since they're a little bit cooler, their cholesterol levels are lower. After that, chicken is lower in content. And then the lowest are fish, because fish that come out of the ocean is lowest in temperature, so their body temperature is lower, so they have a much lower cholesterol content. So that is why highest to lowest. So eating more chicken and fish would be ingesting less cholesterol than eating any beef or pork.
That's all I eat is chicken and fish.
Yeah. Okay? Unfortunately, we're animals.
I'm about to finish.
So we are animals. People don't like to think about it. We are warm-blooded animals, so we make cholesterol too. So you eat cholesterol when you eat any kind of animal product, but we are animals. We make cholesterol.
We animals?
Uh-huh. People don't like to think of it that way, but you are an animal. Okay? So we not only ingest cholesterol in animal foods, but we also make cholesterol. And some of that is genetic. Some people, there are some races that make more cholesterol than other races. Okay? So there is a genetic connection between how much cholesterol a person makes. So high cholesterol might run in your family. And it's genetic. It may not actually be due to what your diet is. It might be a factor, but genetics comes into play as well. So some people, and I have a friend that's Italian, and his cholesterol It's like 300. And I was like, okay. And I mean, he was in his 20s. His cholesterol's 300. And the doctor was like, you have got to really cut out any kind of animal, no red meat, no pork. You need to go to like a fish diet. He was like, this is terrible. But then he was talking to his parents. His parents have the same. His dad has the exact same, we're talking about shapes. He looks, because now he's like 30 years older, he looks just like his dad. And in fact, he has the same genetics. He has the same build. He has the same cholesterol issue. It's a genetics thing. Okay, so some people make more cholesterol than others, and it is genetics. It's based on how your parents are. So if your cholesterol's over 200, it might be that genetically you make a lot of cholesterol. One way you can reduce it is through diet. So just trying to cut back a little on the red meat and pork, that can help lower it some. Interestingly, the second way is you can exercise, because they have shown that exercise increases HDL and decreases LDL. So remember, HDL is your good cholesterol. Exercising improves or increases HDL numbers, so it's going to help to increase the good cholesterol and decrease the bad cholesterol. And that can actually help decrease the amount of plaque on the walls of blood vessels. Now, it doesn't happen overnight. So it's not like you're like, I'm going to start walking. And next week, my cholesterol will be great. It's not going to happen. You're talking about this has to become like kind of like a lifestyle thing. Okay, so you need to do this for months before you really start to see an effect. And it's because if you're exercising, then you're building muscle. So that means that you're going to need to send cholesterol to muscle cells to help strengthen and build membranes. So therefore, cholesterol has a destination. It's not just circulating in the blood doing nothing like the LDL does. So if you go to the doctor and they say your cholesterol is 250, you need to start taking this statin. Statins are things like Crestor, Lipitor. These are chemicals that actually suppress cholesterol production by your body. So it stops your body from making cholesterol. So it takes that part out of the equation. The problem is, yes, there's going to be less cholesterol made by the body, but they have shown that these medications can have some bad side effects. These medications can cause terrible leg cramps. These medications can cause liver damage. So if you go on Crestor or Lipitor, you need to go and have your blood checked every 6 months to make sure that your liver enzymes are normal. Because these enzymes in some people, these medications in some people can have a negative effect on liver function. So you really have to consider risk factors. So if you go to the doctors and they say your cholesterol is 250, first question is, well, what's my blood pressure? Right? So if your blood pressure is 120/80, your blood pressure is perfect, but you have high cholesterol. Okay? I would be more concerned with high blood pressure because I'd be more concerned that there's already vasoconstriction, that blood is not flowing the way it needs to. Next thing, anybody in your family ever had a heart attack, a stroke, hypertension? Okay? Are there other family members, direct family members, so parents, siblings, aunts, uncles, any that are within like one generation? If you see that, that's considered a really big risk factor. So having family members with history of heart disease, that puts you at a risk factor that elevates it, and really the statin may be the way to go. But like I will say in my family, we have like rampant alcoholism because my mother is an American Indian. So we have alcoholism, but we don't have any heart disease. Like nobody in my family has ever had a heart attack. No one, not on either side of my family. Okay. My grandfather had emphysema because he like smoked like a freight train, and he worked around a lot of dust, ended up with emphysema, COPD, and that was a negative disease, but no heart disease in my family. So if I went to the doctors and they said, your cholesterol is 250, I would say, that's fine. I will cut back on my red meat and I will up my exercise and I will get it rechecked in 6 months because the side effects of those statins can be pretty bad. But if you have a family history of heart disease, if you yourself have hypertension and you have high cholesterol, then the statin may actually be warranted. Just don't jump to take them if there isn't enough of a risk factor for it. Because some doctors, I firmly believe, just like to write a prescription and send you on your way. And there may actually be other things that you can do that are a whole lot healthier. So the friend that has the cholesterol of 300, his father does, but his father has had a heart attack. So it doesn't have hypertension himself, but because of his father, he is on a statin. So he is trying to maintain and control it. But then he also likes to make like cheesecakes and stuff like that. So, whatever. Okay. So that's really like the whole reason that cholesterol, you need cholesterol because you need it to make sex hormones. You need it to be able to make your stress hormones. You need cholesterol to stabilize the cell membrane. But too much cholesterol can have this negative effect and cause plaque buildup and lead to issues like heart attacks as well as strokes. Okay, that finishes chapter 7. On to chapter 8. Chapter 8. I'm going to start, maybe, there. Chapter 8 is all about solutions. So solutions are mixtures. Right? So we've talked about mixtures. So this isn't something that's brand new, but these are specific mixtures and sort of like measured mixtures. So solution chemistry is what this chapter is all about. So to start with, a couple of terms. A solution is a mixture. So a solution is going to have a liquid with substances mixed into it. The substance that's found in highest concentration is called the solvent. So the solvent is in highest concentration. For us in the body, the universal solvent is what? Water, right? Remember we talked about that last chapter. The universal solvent in the body, water. Everything that is liquid in the body, water is the solvent. So this is everything from your saliva, mostly water, to stomach acid, mostly water, to the fluid inside of your cells, mostly water, okay? So water is the solvent. And then the stuff that's dissolved is called the solutes. So solutes are always found in lower concentration, okay? Solutes are the components in the mixture that are in lower concentration. The solvent is always found in the highest concentration. And for 99% of the time, the solvent is going to be water because we're talking about living systems. So they're a mixture. So remember that mixtures are things that are physically combined. So if you take sugar and dissolve it in water, you make sugar water. Right? So that sugar is not chemically connected to the water, it's just floating in it. Because sugar is polar, water is polar, like dissolves like, so they mix just fine. If it is what they call a true solution, okay? A true solution is one where the solutes are very small, the solutes will completely dissolve, you cannot see them, and they do not separate out, okay? So when thinking about a true solution, think of like sugar in water. Think about salt in water. So you can't see it. So you have water, put a spoon of salt in it, stir it up. It dissolves. You can't see it. You can't like hold it up and see any little salt particles floating around. It completely dissolves. It does not separate. The particles are very small. They have to have the same intermolecular forces. They have to both be hydrophilic if they're going to mix with water. They would have to both be hydrophobic if they were going to mix together. Most of the time they're like transparent so you can see through. They might have a color, right? Like if you have like Gatorade. You hold up Gatorade and look, it's got color in it. But if you look at it, you can like see through it because it's got salts, it's got sugars in there, and then it's also got some food coloring to give it color. So most of the time you can actually see through it. In fact, most of the time you could actually change the amount of solute. So like how many people like no sugar in their coffee? How many people like a spoonful of sugar in their coffee?
I like black coffee too sometimes.
That's me. I'm like gotten to the point I don't drink it. But how many people like at least 2 sugars in their coffee? How many people like to have like 4? That was my youngest child. My youngest child would be like, do, 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 do. And I was like, what are you doing? Like, you were drinking like coffee sugar. Like it is, I think sugar is the solvent here. Like it was so much. Like sweet tea, that child loved like sweet tea. She'd be like, this is really good. And I was like, I couldn't handle it. I was like, I need some ice. I need more. Yes. So you can change, for the most part, you can increase or decrease the solute. So you could have a little bit of sugar or a lot. You could have a little bit of salt or a lot. So as long as it dissolves, it's called a true solution. Some solutions can be liquids, some can be gases. Most of the ones we're going to talk about, they're all going to be liquids. But there's 2 other kinds of solutions. So we can have solutions that exist as what they call colloids. So you're actually going to work with one of these in lab tonight. So in lab, I have a starch solution. So what I did is I measured out starch, I put it in water, and I boiled it. And that's the only way, like you have to boil flour in order to get it to dissolve, like if you make gravy. So you know how it's thick? So a colloid is when you have a big particle. So they're big solutes, but they do dissolve. They dissolve in the solute. So they do dissolve in the solvent, and they stay mixed, but they will make your solution thick. So good examples is like whole milk or cream, gravy. So cream has fat in it, gravy has starch in it, Jell-O. Okay, so like I don't know how long it's been since you've had Jell-O, but Jell-O, like it's solid. Okay, but there's a lot of water in it, but it has collagen in it, and that's the reason that it's thickened. But they totally dissolve. You can't see any stuff in it. It looks completely transparent. Those are all good examples of a colloid. So the particles in this are big, but they are still going to able to dissolve in the solvent. They still have similar intermolecular forces. But what about a suspension? A suspension, the particles are really big. Very large solute particles. And because they're so big, they can't dissolve. They're going to separate out. So can you think of an example of something that was described as being a suspension? Italian dressing? Okay, yeah. So those great big huge like herb particles, that's a suspension. You shake it up, and if it sits, they all kind of settle out because they're so large. They don't dissolve. So like the Italian herb dressing, do not stay mixed, so they end up forming a heterogeneous mixture. When I think of a suspension, I can think of like dirt and water. So if you have a cup of water and you put a spoon of dirt in it, you know, like some of the particles float on top, some drop to the bottom, but it gets kind of cloudy looking. But if you let it sit, all those particles will settle and you'll actually see the water. And then you can go and like mix it back up and it gets all cloudy again. So dirt and water. The dirt doesn't dissolve. It doesn't stay dissolved, but if I shake it, I can make it mix. One of my children's favorite medicines is a suspension. So it's this pink liquid. Amoxicillin. So did anybody else like amoxicillin when they were kids? My children would be like, yay, we get amoxicillin. And I was like, I don't even understand this. They would get like an ear infection or they would end up having like strep throat. Doctor's like, amoxicillin.
Well, now as an adult, they don't put that flavor in it.
You just take a pill.
They won't
They
even give you.
The pink juice. They loved that. Like that would be like a highlight of being sick for them. I was like, this is very strange. And it was, but when you go to the pharmacy and you give them your prescription, they go and get this bottle of amoxicillin off the shelf. And inside of that bottle is powder.
And they mix it.
And they add what?
Water.
Water. So the pharmacist adds a specific amount of water, caps it, and stands back there and shakes it 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 and shakes it. It doesn't dissolve, okay? Because what does it say on the bottle? Shake before dispensing. So it's a suspension. So all of the medicine drops to the bottom. So you've got to make sure that suspensions, you shake them before you distribute it, because otherwise you're not going to get the right concentration of the solid, okay? So amoxicillin.
It's a big pill too.
Yeah. I can remember when the older one, like she had like strep throat or something. And so she ended up having to take, she was like a teenager and they gave her that. She was like, what? No pink juice? I was like, it's because you're too old for pink juice.
Stuff up until I was like 19.
You were like, I want the pink juice. All good examples. So these are all good examples of suspensions. I really like this image because this shows how blood is all three. Okay? So blood, if you collect a sample of blood, you put it in a tube, and then you put it in a centrifuge. So you remember the centrifuge that we used in the banana lab. So the centrifuge is really, it's a machine that can spin your sample around, kind of like a washing machine. Washing machines pull all the water out. The centrifuge, everything heavy goes to the bottom of the tube, okay, which is towards the outside of the centrifuge. And then anything that's light, less dense, will end up collecting at the top. So when we did the banana lab, we had sugar water that ended up at the top, and then the starchy brown muck ended up all the way down at the bottom of the centrifuge tube. Remember that? So in that lab. So that's the same thing. So blood is a suspension. So if you look, see this blood has been centrifuged, and you see this yellow layer, and then you see this red layer. So this yellow layer here, this is the fluid of the blood. This is plasma. So the fluid component of the blood is plasma. What is the red stuff down at the bottom? What is floating in blood that makes blood red? Red blood cells. So these are packed red blood cells. They are heavier than the fluid, and that's how you can get them to separate out. I do have to say, this person is ridiculously anemic, okay? So if you know anything about blood, human blood should be about 45% red blood cells and about 55% plasma. So looking at that tube to the right, what would you say?
They have low iron.
Like they're at like maybe 25 or 30%. This is some seriously low. I was like, why would anybody use this as an example in a textbook? I was like, this person's sick. Like this person needs some serious, they might need a transfusion because it really should. Almost half the tube should be red. Half the tube should be that light yellow, clear liquid. That's plasma. Okay, so those red blood cells, the only reason the red blood cells and white blood cells and platelets, they're just such a small amount you don't see them. All of those blood cells, they are suspended in the blood. And why don't they separate out? Because your blood is always what? No. Why wouldn't all the red blood cells like settle out? What is your blood doing? It's constantly moving, right? So as long as the blood is moving, the blood cells stay suspended. So what happens when you die is the blood stops moving and all those blood cells end up collecting.
They get
Okay.
all spent.
They're all gonna end up coming out of suspension, okay? The only way to keep a suspension mixed is by shaking it, by agitating it. So your red blood cells, white blood cells, and platelets stay dissolved, stay mixed in the blood. Well, they don't stay dissolved. They stay mixed in the blood because of the fact that the blood's constantly moving, okay? So red blood cells, white blood cells, platelets. These are all suspended in the blood. And it's always moving. But that plasma, which is kind of like, see how it looks kind of like, they say it's straw colored, because it's kind of yellowish looking. If you felt plasma, plasma's thick. So which of those three components, which of those three types of solutions makes it thick?
Colloid.
The colloids. So there is actually a colloid in plasma. So the colloid in plasma are plasma proteins. So plasma has proteins. And proteins are large molecules that stay mixed, but they actually make plasma like thick, more like gravy. There are albumins. The job of albumin proteins in plasma helps to keep water balance. There's also immunoglobulin proteins. What do you suppose they are? From the name. They're part of your what? Immune system. These are your antibodies, right? So antibodies are these proteins in the blood that stick to things that are foreign that you've been exposed to. So immunoglobulins, these are antibodies. So when you go get your flu shot, they give you a vaccine, and it contains little tiny pieces of the virus that can cause the flu. It doesn't contain the flu virus. It just contains some of the pieces that are there. And so your immune system finds those pieces, says this is foreign, and makes antibodies.
Well, mine don't, because every time I get the flu shot, I get the flu.
Okay.
You might have symptoms, but I have a hard time believing that you get the actual flu.
I always get the flu every time I get
I believe.
Then you have to be exposed because you can't get it. You can't get it from the vaccine because the vaccine isn't even the virus anymore. The vaccine, so you have the little virus particle and they like picked off this piece and they like made a vaccine from it. So it's not even the entire virus. So that's the part, it can't give you the flu, but it can make you feel bad.
Every time I not got the flu shot, I've not gotten the flu.
Well, that's like a throw of the dice. I never got flu shots until I started dating the guy that's now my husband because he works in an ICU. And I was like, yeah, I don't even know what you're going to end up bringing back to me. So that's when I started getting a flu shot. I'm never around people that do any of that. And then I was like, ew, and you did what? Ew. Yeah, I got to go get a vaccine. But those are what antibodies are. So if you get exposed to something foreign, your white blood cells, specifically B cells, they figure it out and they make antibodies. And antibodies will stick to things that are foreign. So how many people have had chicken pox? Yep. You've never had chicken pox? Have you had a vaccine? Okay, good. Because you can't go into nursing unless you have you've got to get yourself titered. When they talk about a chicken pox titer, they actually can measure the amount of antibodies in your blood that will react to chicken pox.
You know, the chicken pox stopped it in the 90s.
No,
Well, you had to be in the, what is the 2000, early 2000s?
Yes, I would say maybe about then. That's just because they started vaccinating kids for it.
Kids in the
Okay?
2000s.
My kids had it, okay, but my kids were born like right around 90. So my kids were, one was 9 and one was 7. So they both had it, one right after the other one. It was great. Chicken pox everywhere. And all of us had it. Like none of us had vaccines. But about 3 years after, they started putting the chicken pox vaccine into the normal. So if you are younger than 29, 28, then you probably had a chicken pox vaccine. And so maybe you haven't had chicken pox. But if you're going to go into nursing, you have to actually go get a titer to make sure that you have the antibodies that can protect you against chickenpox. Because the big issue as an adult, if you get chickenpox, you get really sick. A lot more sick than a 5 or 7-year-old kid does. They get sick, they get all the pops all over them, but then they're good to go within 7 days. Adults, you're looking at a good 3 weeks. It's like it's like the shingles thing, yes. So antibodies are floating in your blood. Everything you've been exposed to, you have a little collection of antibodies floating in your blood that will attach and recognize something that's foreign. If you've been exposed to it before, like if you've had a vaccine or if you've had the chickenpox. So I have the chickenpox, I have chickenpox antibodies in my blood that's always there. And so if I'm around somebody that has chickenpox, those antibodies respond, trigger an immune response, and keep me from getting sick. Last one, then we'll quit. So the last one is that you have clotting proteins. So what do clotting proteins do? They help you to stop bleeding. So clotting proteins are going to clot the blood if you cut yourself. So you have proteins, and these are also completely dissolved in the blood. The only time they become solid is when they form a clot. So like if you cut yourself and you see this blood flowing out, and you keep dabbing it and dabbing it, eventually it sort of slows. And then it kind of, if you've ever like studied your scabs and your wounds, you get almost like this jelly kind of like red stuff that forms over that cut and it stops bleeding. That is a clot. Okay? And so there's proteins in the blood that help to do that. So we'll pick up finish the bulk of chapter 8 on Monday. Probably finish it then next Wednesday, start chapter 9 as well. Because this is a lot. Like there's a lot of like math parts that we're going to do next time. So do make sure that you come ready to practice that next time. But I'll give you all of the steps that you got to do for stuff.